Hello everyone. Today's video is the first in a series I'm preparing on a body of work known as vortical impulse theory. So for this first video, I just want to introduce what is vortical impulse, and generally speaking, it's a very useful concept in fluid dynamics, and it is related to fluid dynamic force. So we're going to talk about how it is that it's related, and we're going to talk about how vortical impulse is related to the more familiar concept of momentum. So firstly, let's talk about how momentum is related to force, because we're all fairly familiar with that. So we need to define a control volume. We're going to do a control volume analysis. I'm just drawing this rectangular, but I'm actually considering an unbounded fluid domain. So externally bounded by S infinity, which is out at infinity. The unbounded domain, or the volume, which could be 2D or 3D, is going to be called V infinity. And we're going to have enclosed and submerged in the fluid some body whose volume we will denote VB and whose surface is SB. And this is sufficient now for us to derive an expression for force based on the velocity field surrounding the body. So I won't show the derivation. I'll assume that you're familiar with this type of control volume analysis. So now the force acting on the body, I'll just draw that here. This would be the force that the fluid imparts on the body, is going to be equal to, well, the first term is going to be a volume integral over the full domain of the velocity, u. So this term here is simply momentum, or the integral is momentum if rho here is density. This is specific to an incompressible fluid domain, which is why I was able to take density outside of the integral. We'll have a surface integral as well over S infinity involving the flux of momentum across the outer boundary. And we will have a term that involves the stresses, the normal and shear stresses acting on the outer control surface. So that'll involve pressure P and the viscous stress tensor. I'm using the two lines to denote that this is a tensor. And this is the general expression to relate the velocity field and pressure field to the force acting on a submerged body. Now, this kind of analysis can be very useful in a lot of applications, but there's something left to be desired. So in many engineering applications, we'll want to be able to relate what's happening to the body. So the body may be moving, accelerating, it may be even morphing, and we wish to know, just based on the motion of that body, what is the force instantaneously acting on it. For many applications, this is very useful. So in order to do that, this expression is not terribly useful, because we can't just know the motion. We need to know the motion and then solve for the entire flow field, the pressure and the velocity, over this domain in order to put all the variables into this equation here. So for many applications, this isn't as useful as we would like. One aspect that can be particularly difficult to deal with is the pressure field, because in an incompressible flow, we have the pressure changing more or less instantaneously all throughout the domain when we have a change at any other part of the domain. So making physical arguments about what the pressure field is doing can be difficult. So with the goal to get an expression for some applications that relates body motion and geometry directly to force without having to solve, and hopefully that removes the need for pressure information, now we'll move on to the concept of impulse. So impulse shares a property with momentum. I'm going to define vortical impulse by the variable IV, and the property it shares with momentum is that at least a component of the force is proportional to the time rate of change of vortical impulse. So in that way, it is analogous. And I'll give the definition mathematically first, and then I will show how we get it into that expression above. So the mathematical definition depends on a fluid domain, and it is going to be this, which is the first moment, the first vectorial moment of the vorticity field. So here omega is the vorticity field, x is a position vector, and yes, so eventually now we can get this expression into the equation above. So how are we going to do that? Oh, and I should mention here, n is the dimension of the space. So n can be either 2 or 3 for looking at 2 or 3-dimensional cases. So to relate momentum and impulse, we use an identity, which does so directly. So for any continuous vector field, so U here could be any continuous vector field, this integral over a volume is going to be equal to the integral of x cross the curl of that vector field. So in the case of velocity, this is the vorticity that we're recovering. And we're going to be introducing some extra surface integrals. So on the full boundary of V, we also have this x cross n cross u that we will need to deal with. Oops, actually I need to change that sign here. So this is the sign convention with n pointing out of the domain on all sides. So in our particular case, I'm just going to be careful with the sign of our normal vectors. We'll have it pointing outwards on S infinity, but because it's sort of strange to have an inward facing normal here, I'm also going to have n facing outwards on the body. So what that is going to mean is that this is going to be equal to I'll introduce the definition of vorticity here, and we're going to have minus 1 over n minus 1, this integral over S infinity. And we're going to have to introduce with the opposite sign because of our convention the same integrand but integrated over SB, the body surface. Okay, so now we can substitute this back in to our expression for force. Let's see what that looks like. So I'll come down here, and voila, there it is. So I've just substituted that identity into the expression for force. Now I've removed all of the densities here. So without loss of generality, I should say this is for the case that rho is equal to 1. Now we can do some further simplifications. At first glance, this does not look like an improvement in terms of simplicity or understandability, but let's consider the case that we said that we're looking at, which is the unbounded case. So in that case, one of the key contributions in a thesis by a man named Flavio Noca in 1997 is to show that even if we don't have means to show that pressure vanishes on the outer surface integral, or that this integral vanishes, he did show that these two terms in the unbounded case cancel exactly. And the way he did that is substituting the Navier-Stokes equations in for u here, moving the time derivative in, and rearranging and showing that these cancel. So we've achieved one of our goals that I stated at the outset, which is to remove pressure from the equation. So now we're left only with velocity and gradients of velocity. Now for the unbounded case, again, in the additional special case that the total circulation within the fluid domain, so I should say the total circulation encompassed by S infinity, including the body and the fluid domain, if that total vorticity, let me do that better. If that total vorticity or vectorial circulation is equal to 0, in that case, we can also show that this term tends to 0. And if the onset of motion happened a finite time ago in this infinite domain, then none of the vorticity will have reached the outer surface, and so there will be no viscous shear acting. And so this term also vanishes because omega, as well as the gradients of omega, are 0 on S infinity. So now, let me just put a box around the remaining terms here. Now we have an expression that looks substantially simpler, and we can start to talk about how the evolution of the vorticity field, which we can make arguments about based on empirical observations, how that directly affects the force. So now we have here, we've introduced impulse to be part of the force expression, and we also have this integral now over the body surface, which in future videos I'll talk about how we can deal with that in a useful way. So I will leave it at that for today. We have this useful starting point for a large class of unsteady, unbounded, incompressible flows. Thanks for watching.